resume.
Okay. All right. So you can see the soil stabilization in that mixture, right?
Yes, sir.
Okay, good. So again, welcome back. So now I'm going to talk about the soil stabilization. As I mentioned earlier, there are four major soil treatment methods. One is the mechanical one is the hydraulic modification, get rid of the water, and then the chemical modification, and last one is the inclusions or using geosynthetic. So today I'm just going to talk about the soil stabilization with admixtures. Soil improvement with admixtures, obviously we need to add some chemicals into the soil. So basically, you need to add any type of admixture. So most of the time, we use Portland cement, ordinary Portland cement, or lime, or fly ash, or bitumen, or any other material. So basically, if you talk about the chemical stabilization mixtures used when mechanical method of stabilization is inadequate. So when you try with mechanical, it is not working. In that case, you can use it. Or replacing an undesirable soil, the desirable soil is not possible. So, and it's too expensive. So in that situation, you need to use this soil stabilization. So just for example, we have a huge depth of soft clay, and we cannot just one method we mentioned earlier that the field replaced with a good soil. So sometimes it's not possible to, because the depth is too high, so you cannot replace. And then you can just improve only some portion of the topsoil by using chemical admixtures. So that is a viable option. So again, sometimes people use, as I mentioned, so like all these different type of chemicals, Portland cement, lime, or fly ash, or sometimes in combination of these, 2-3 chemicals together. Okay. So with the admixtures, improving so basically what is happening, so when you add these chemicals into the soil, there is a chemical reaction, obviously. There's a chemical reaction takes place, and you need to understand that what is happening into the soil and what is forming after this chemical reaction. So improving the engineering property of the soil is often simply referred to the soil stabilization. This is soil stabilization. Some admixture of agent is good stabilizing some agents, some is not. So just for example, if you're using cement, for example, it is good for all type of soil. But if you're using lime, so that is not good for gravel type of soil. So it's only good for clay, for clay type of soil. So that's why it says some is good, sometimes it's not good. Agent also, stabilizing also undergo different reactions and require different conditions to reaction takes place. Again, we'll talk more about that. Therefore, it is important to understand this. So chemical reaction, what is happening when you add soil, you need to know the chemical composition of the soil. You need to know what are the stabilizer chemical compositions. And then when you mixing it, what type of reaction takes place. And then from there, you can choose what type of soil is the stabilizer is the most suitable for a particular soil. And obviously, you need to do a lot of trial and error test. And then you can find out how much is optimum. So the most commonly used, as I mentioned, the most commonly used the Portland cement, lime, fly ash, silica fume, blast furnace slag, or sometimes called the granulated blast furnace slag, calcium chlorides. So what any type of stabilizer you use, what are the different reaction takes place? So just for example, using cement, what is the cement? We add water into that. What is the different reactions? Pozzolanic reaction between the calcium hydroxide and pozzolanic minerals of the soil. Again, you need to understand what type of clay mineral present. What type of clay you are trying to stabilize. What type of clay you want to stabilize. Whether it is again, clay is less than 0.002 millimeter particle size, and the silt is 0.075 to 0.00 or 75 to 2 microns. But the main thing is that clay also, there are different types of clay, right? So whether it is illite, kaolinite, bonbonite, bentonite, depending on the type of clay, whatever different mineral present in that clay. And so you need to use different stabilizing agent, and then also in combinations, and sometimes use what are the different doses. So, and then also, as I mentioned, so the ion exchange reaction takes place also. So what is the chemical reaction takes place? That's very important. So in order to understand the chemical reaction between the soil and the stabilizing agent, we need to understand the composition of the agent and their reaction with water. So water is the one that the reaction takes place, right? So in general, most of the cases when the particles are fine, the surface area is more, then the reaction will be more. Okay? So reaction will be more. Temperatures plays an important role. So obviously, the higher temperature, the reaction is more. We'll talk more in geopolymer salt stabilizations. So low temperature impact the photogenic activity reaction negatively. So we need more higher temperature for more chemical reaction. So the minimum, the purpose of mixing of these additives. So again, for any type of stabilizer, when you use to clay type of soil, so what is happening? Increase the strength and stiffness, increasing, reduce the compressibility and deformation, reduce liquefaction potentials, control shrinkage and swelling, reduce permeability, seepage and water pressure, reduce slope instability, reduce erosion potentials, and reduce the potential detrimental environmental effect and the stabilized west side. Again, all these things. It's a very general purpose of this any mixing or salt stabilization mixing. So first thing is I'm going to talk about the cement, and then we'll talk about the lime and fly ash and GTBS. Okay? So first thing is cement. So we need to know for what type of cements are there. So there are normal cement, there are modified cement, high early strength cement. Sometimes we need it. There are low cement, and there are sulfate resistant cement. So sometimes you need to see that there are some soil has a lot of sulfur or clay. So if you use cement, then there is a mineral form, the ettringite, and instead of stabilizing it, so that the volume is going to increase, and that is not good. So there is a limit how much the whether. So in that case, what you are going to do instead of cement, you need to use some other type of material. So that's why there are sulfate cement is also there. And suitable soil type. So cement can be used for sand and gravel, mostly granular type of soil. Also suitable for fine-grained soil. So obviously cement is suitable for all type of soil. So obviously if it is a clay type of soil, you need to add more quantity. We need to add more quantity. Low to medium plasticity, plasticity index is less than 30. So can be used also. So now when you add cement to clay or soil, what are the different reaction takes place? You need to understand that. So ion exchange reaction takes place. There will be flocculation, there will be pozzolanic reactions, carbonation reactions, and then also cement hydration. So that is the most important, cement hydration. So now, so when you talk about cement, you need to understand what are the different, how the composition of the cement itself. And then also the reaction of the cement and water to form cementitious compound, that is calcium silicate or calcium silicate hydrate, or which binds that together. So it is when you add cement with clay, so it's a calcium silicate hydrate, calcium aluminate hydrate. These are the two minerals formed, and because of that, or ettringite or monosulfate aluminate. So these are the different mineral form. Because of that is glued together. Okay. So major gain of the soil cement treatment of the soil is increase, again, as I mentioned, the general one, increase the strength and stiffness, better volume stability, less moisture sensitivity, control of frost and heat, and increased durability. Cement. Also these days, people are more concerned about using cement because the production of cement itself generate a lot of CO2 and greenhouse gas. And so people are going towards like a calcium sulfur-aluminate cement instead of Portland cement, some other cement type of material, cementitious material. So as I mentioned, the reaction in general, we need to check. The Portland cement reacts with water to provide high strength immediately. So again, there are different types of cements are there. So this is the immediate initial setting time cements, immediate, that's quick cement. That can reaction will be much faster. Then the lime, so these are just general reactions. This is with the cement, immediately it reacts. So lime, it reacts with water. And again, what type of lime you're using? You use calcium hydroxide and provides no strength gain itself, but reacts with pozzolaniform soil to provide strength gain slowly. So what is happening sometimes is pozzolanic material. So just for example, we have a fly ash. This is class A, just for example. We have So this is pozzolanic materials. You need to add a little bit of lime, then it is going to react. Okay? So pozzolanic agent like fly ash, silica fume needs calcium hydroxide, for reaction. If enough CO2 is not available, the addition of this agent will not do any good. So again, the blast furnace slags need to activate before it can react. So again, these are the different. So we need to check the chemical composition first. You need to check the chemical composition of the soil, and then you need to understand what are the reaction going to take, and then you can use that type of stabilizer. Reaction product from any agent mainly consists of calcium and siliceous compound with smaller amount of aluminum, iron, and other elements. So this is Portland cement, as I mentioned. So the particle size is 1 to 100 micrometer. And I'm not going to talk about how the cement is produced. Basically, it's a limestone and clay and put it in a clinker with high temperature, and it rotates. And then obviously we add some gypsum to delay the initial setting time. There are for the concrete, people use different other retarder, but for the soil is already there, type of gypsum. So surface area is higher, so more surface area means it is more reactive. Typical composition of the cement is, you see the calcium is the one that binds together, calcium oxide, 60 to 75%, 60 to 70%. Then silica is 17 to 25%. Alumina is 0 to 6%. So silica, alumina, iron, manganese, magnesium, iron, sulfur, these are the few things. And then calcium, we generally denote C, and silica is denoted by S, and the alumina is A. So when you say that CSA, so calcium silicate aluminate, these are the different abbreviations generally used. So cement is cement hydration. So there are 4 main components. I'm just going to go here. The composition of cement is tricalcium silicate, dicalcium silicate, tricalcium aluminate, and tetracalcium aluminum ferrite. So these are the 4 main components of the cement. And then tricalcium silicate and dicalcium silicate constitutes 75%. So when you add water, so this dicalcium silicate and tricalcium silicate is going to react with the water over here, and then it is forming calcium hydroxide is 25% of the hydrated cement, and then calcium silicate hydrate 50%. So that is the heart of the concrete. So calcium silicate hydrate, we call it CSH. Okay. So and the reaction of this tricalcium aluminate to form tetracalcium aluminate hydrate. So as I mentioned, so these are the 2 main things: tricalcium, dicalcium when you add it to the water, and then tricalcium aluminate, it will be forming tricalcium aluminate, and then tetracalcium aluminum fluorides also. So over here you can see tricalcium silicate hardens quickly. This is responsible for initial setting or early setting cement. So you can play with these different compositions, and you can make different type of cement. So C2S, dicalcium silicate, hardens slowly, and it contributes gain after 7 days. Tricalcium aluminate is a large amount of heat during cement hardening. Tricalcium aluminate fluorides hydrates quickly, but contribution is very little towards strength gain. So basically, it added to reduce the temperature of the clinker itself. So as I mentioned, so basically there are different components of the cement, and then how it reacts with water. So now when you add with the soil, you need to see the chemical composition of the soil itself. So soil is mostly the silica and alumina, correct? So silica, alumina, iron, there are 3 things. And then also how when you add these chemicals, how the chemical reaction takes place. And then finally, it is going to form calcium silicate hydrate, calcium aluminate hydrate, or calcium silicate aluminate hydrate, or maybe a tringite, or maybe the calcium monosulfate aluminate. So all components start reacting concurrently at different rate. As I mentioned over here, tricalcium silicate and dicalcium silicate, these are the 2 things, react first. And then within first few minutes, cement releases some ions and some silicates, primarily tricalcium silicate, starts reacting. A tringite formation, this is the one the mineral formation starts, and heat is generated. And after 10 to 20 hours, it is difficult to water to penetrate the reaction. So basically, it is forming a calcium silicate hydrate gel, and the reaction and the heat evaluation subsides, but formation of ettringite continues. Okay. So again, ettringite is not good for sulfate when the sulfur, the clay present a lot of sulfur. Then ettringite is structures. Basically, it's like a flower type of structures. It increases its volume. That is not good. So when no more sulfate is available, gypsum provides the sulfate, the ettringite converted into monosulfate aluminate with a denser than ettringite. This is much more stable. Okay. So mostly when you add cement, so 50% of the cement reacts in 3 days, 60% in 7 days, and 90%. So that's why most of the time for any, even in concrete also, we calculate the strength after 7 days, 14 days, 28 days, like that. So initial, so that's the reason. So 50% cement reacts within 3 days. Okay? So hydration of calcium, tricalcium silicate or dicalcium silicate, as soon as water is added, calcium ion is released rapidly and hydroxide ions is formed. pH is going to increase. So that's when the pH is 12 in few minutes. So more pH is better. So it's the alkali and silica, because the silica is the alumina and the soil contain the alumina and silica, correct? So when pH is increases, then it will dissolve the silica and the reaction takes place in forming a gel, calcium silicate hydrate gel. So when the calcium hydroxide ion concentration reaches a certain threshold, calcium hydroxide crystallizes out of solution, and then a extremely fine poured calcium silicate gel is formed. Okay, and the specific surface of this gel is around 350 meters square per gram compared to the cement itself. So as I mentioned, the more surface area, reaction is more. Okay? So as this layer grows, water must penetrate through the layer and to get to the unhydrated tricalcium silicate and must diffuse through the gel. So basically, and then calcium silicate gel is very strong and considered the heart of the concrete, as I mentioned. And C2S, dicalcium silicate, reacts the same way, but at the slower rate. So again, as I mentioned, that which one is reacting first, that the dicalcium silicate, tricalcium aluminate, tetracalcium aluminum fluoride, and what type of clay minerals are there. Hydration of tricalcium aluminate, there is no sulfate in cement, no gypsum is going to react with the water to form the calcium aluminate hydrate. And tricalcium aluminate reacts with the water again to form ettringite. And then again, ettringite is stable only for excessive, as there is excessive sulfate. Since the concentration of sulfate falls 24 hours, so obviously ettringite is converted into monosulfate. This is much better. And then, so these are the different reactions takes place, with the different composition of the cement itself. So now, so when you add cement to soil, what is happening? Basically, this is common for all stabilizer. And then, so reduction of the plasticity characteristics as made of a plasticity index, that is liquid limit minus plastic limit. Reduction in the amount of silt and clay particles, it is forming like agglomerations since particle size is increasing. Reaction increase in the California bearing is a test that is going to increase. Increase in the CS strength, that is UCS strength is also going to increase, and decrease in the volume change properties, obviously. Then that is the cement. Now, if it is a lime use, what is going to happen? So lime is, again, there are different types of lime. So one is like a limestone, that is agricultural lime, so we don't want that. So there is a quick lime, there is a hydrated lime. So and then composition of lime is basically the calcium oxide is a lime. So calcium oxide is the main composition, 90 to 94%. Silica is 1.5%. Alumina is 0.8. Magnesium oxide 1.7. So obviously, the quick lime is sometimes divided into two categories: hard burnt lime and soft burnt lime. So based on the residual CO2 left after calcinations. So over here, Quicklime is basically calcium oxide. It's in dry form. So when you calcium oxide added with water, that will be forming a calcium hydroxide. That is hydrated lime. There's a hydrated lime or sometimes it's slaked lime. And then the dolomite, that is calcium or magnesium oxides. And then we have agricultural lime, that is calcium carbonate. So we don't want that in agricultural lime for the soil stabilization. Sometimes the lime also used because when we add lime to the clay, so it generates heats. And sometimes instead of actual stabilizations, it can be used as a modifier just to reduce that the water content from the clay. So the quicklime is more effective than the slaked lime in terms of handling and transport. Agricultural lime is not suitable for stabilization. Dolomite lime is not usually used as effective as hydrated or quicklime. So now again, what are the reaction takes place? So basically, lime is made from limestone and then consists of calcium carbonate. So basically, when you calcium carbonate, we heat it. So it will be forming CaO plus CO2, correct? Calcium oxide plus CO2. CaO is basically formed during the reaction. It's called the quicklime. So basically, that's why it's heated. So that's why it's the burnt lime also called. Slaked lime, you have to add with water, and then it's forming calcium hydroxide, formed in the slaked lime or hydrated lime, or sometimes in construction lime. In US here, most of the time people use like quicklime. It depends. Sometimes people use hydrated lime. Both has advantage and disadvantages. So hydrated lime commonly used to stabilize soil in US, hydrated limes, whereas quicklime is commonly used in Europe. So again, it depends. But I know over here in Southern Illinois, people use this, the quicklime also. The less pure form of lime are also available and sometimes used for stabilizing agents. So sometimes people are using even lime clean dust or cement clean dust, from the cement industry or lime industry. It's not the actual lime, but it's a waste, and we can use that also for the stabilizing purpose. So hydration of lime, we just mentioned again, quicklime, this CaOH2 plus heat, CaOH2 plus water plus pozolanite will be forming is calcium silicate hydrate or calcium aluminate silicate hydrate. We call it CaSG is similar to one obtained from the cement, but CaSH this contains alumina. Okay, so now when we add lime plus CMOS, there are short-term reaction and long-term reactions. So the short-term reactions, the hydration takes place quickly, flocculation takes place or ion exchange. Long-term is the cementation and the carbonation. So what is hydration? So basically it reacts quickly to water and producing hydrated lime. So that is CaOH2, generating considerable amount of heat and causing volume increase. Particularly beneficial some moist clay, as I mentioned, it can use for the drying the clay. It's too much of water. So in the placement of lime column and layer, the heat generation and expansion of the lime further enhances the consolidation process. So basically, remove the water. So we remove the water is basically consolidation process. So hydration, then the flocculation. Flocculation, so when mixed with clay, sodium and other cation absorbed to the clay. Again, you need to know that the clay is negatively charged particles and what are the different minerals present and what type of clay you are talking about, whether it is 1:1 clay or 2:1, depending on that clay, and then maybe ion exchange and isomorphous substitution takes place. This change in the cation exchange complex agent affected the way of structural component of the clay minerals are connected together. Lime causes clay to coagulate, aggregate, and flocculate. Okay, and the clay plasticity is reduced because of reaction, and they're making it more easily workable and potentially increasing the strength and stiffness. But again, for clay lime is not suitable for gravel or sand. It is only suitable for clay or maybe a little bit of silt. Cementation, again, the cementation is the main contributor of the reaction of the stabilized soil. Higher the surface area, more reactive is the process. Okay, more reaction will take place. So lime, again, that's the no dimensions. Lime is not suitable to improving clean sand or gravel. Okay? Cementation is, however, limited by the amount of available silica. Again, the silica there are different type of silica. And then when we add, that's why the pH need to be increased. And then the alkali silica reaction takes place. And increase the strength up to a point where all silica of the clay is used up. Okay? Then the last one is the carbonation reactions. The carbonation reaction of lime with CO2 in open air and voids of the ground forms relatively weak cementation agent. So again, if the CO2 is formed, that is inert, so we don't want that. Okay, so CO2 form will not react further with the soil. Okay, so if the carbonation takes place, so CO plus CO2 is forming CaCO3, so we want that. So benefit is the same exactly like for the cement. Also improved workability, increase the strength of unconfined compressive strength, UCS value, or California bearing ratio test value. Improve the volume stability, the sinkage and soiling behavior, drying and wetting behavior, respectively. So basically, it's very basic for all stabilizers. These are the two common things people are using: the stabilizing agent or admixture, cement and lime. These are the two common. People are using these days for the last 15, 20, 30 years that different agent, but you have to be careful while using that different stabilizer agent or waste material people are using. Instead of dumping to the landfill, people are using that. Is much more sustainable, but you have to do the leaching test and other things. Otherwise, it will be a problem in terms of environmental point of view. So amount of lime required varies based on the characteristics of the material that need to be treated and desired degree of stabilization, how much the strength you need. Most of the cases is different people have studied different things. So 2 to 3% of dry weight of the soil is sufficient. So most of the time people use like a 6 to 8%, 6 to 8 to 9% of lime. So if you use more than that, the strength increasing strength is go down. Okay, so depending on the free available silica, right? For stabilization purpose, typically 5 to 10% of the weight of the dry soil is used. But again, as I mentioned, it can be up to 6 to 9%. So how you can find out the optimum lime content? So you can find out how much is the percentage of clay divided by 35 plus 1.25. So this is the given as per the Bargado. So how much is the optimum lime content to stabilize the clay? And also we need to check that, different trials. So you take some clay and then add different percentage of lime and measure the pH. Okay. When you see the pH is at least 12.4, that is the lime percentage generally you need to use. Okay. But this will give you a preliminary study. And then, immediately, then you have to do more tests and to find out so how much is the optimum lime content. So some of the advantages and disadvantages of dry hydrated one. So this is the one, the advantages of dry lime can be applied 2 or 3 times faster than the slurry. This is very quick. But again, dry lime is not is effective in drying out the soil. It's a dry because it's going to react and, it generates heats. And then it dry out the moisture easily. Disadvantage is dry lime produces a dusting problem and thus make it use undesirable in urban areas. Fast drying actions, so dry lime requires excessive amount of water also. So if you are using in hot season, that is not good. Some advantages and disadvantages of dry quick lime. So it's more economical. It contains approximately 25% more available lime. Greater bulk density for small sizes silos. Faster reaction with soils. So these are a few things you need to check. Disadvantage is field hydration, less effective than the commercial hydrator. Quick lime requires more water than the hydrated for stabilizations, which may present a problem in the dry areas, and the gaseous susceptibility to skin and eye burns. Again, quick lime that's the disadvantage. The slurry limes, that is the hydrated lime. So again, the dust-free application is more desirable from environmental standpoint. Better distribution be achieved in slurry. Sometimes if you use dry, the mixing process is not good, then it will be a problem. The lime slurry method, the lime spreading and sprinkling operations are combined, thereby reducing the job. Dry one, you have to spread the lime first and then mix it, then spread water, and then you do the compaction and mixing and compaction. So here, everything is together. Slurry is there, just add it and mix it. The added heat when slurry is made for quick lime speed drying action, which is especially desirable for cooler weather. Disadvantages, application rates are slower. High capacity pumps are required to achieve applicable application rate. Extra equipment required, therefore costs are higher. And then it's not practical for use when the soil is, obviously when the soil is wet, so we can't use that the wet slurry method, right? So this is how it looks like, the spreader, how they spray the dry lime, and then it makes it like it pulverizes, and then you add water, after pulverizes and stabilizes, they compact it, and then add water and then compact it, basically, and then left it for curing. So this is close to my campus. I just took some picture here. So first they spread the lime using this instrument, using that machine. And then this is the main mixer over here. You see, initially it was here, the lime was there. So when the truck is going with the mixer, so inside is the mixing process. And then when it goes, it is already mixed. Okay. So this is already done. You see already one time mixes, they do 2 times. And then this is the same pictures. And then how it looks like, you can see here, there are lime mixtures. This is quite uniform mix of the lime with the soil. Okay. And after the mixing is done and spreading water, they use that the sheep foot roller or compactor. And then when the sheep foot roller is done, the compaction is done, obviously you need to use the field density test. What are the density? And then also later on, you need to collect the soil sample for UCS testing later on. So here, this is the nuclear gauge test. And to determine that how much is the field density, you can use any method. You can use even core cutter or a sand replacement method or water replacement method, a rubber bearing method. So lime stabilizations, as I mentioned, so most of the time is a mix it. This is one is just shallow mixings. There are deep mixings. You can make a lime column also. So these are the different equipments. Generally completed lime column. So what is a soft soil? There is a mixer. Inject unslacked limes and then mixing tools. And with the compressor, they just mix it and then forming a solid lime column and then just lift it up. So it is basically from the bottom and then go up. Okay. So lime columns are extensively used in Sweden, Norway, and Finland, following purpose to improve the total and difference in settlement with lighter structures, increase the settlement rate, and control the settlement relatively heavy structures, improve the stability of the embankment and slopes. So more than 1 million tons limes are used in US for a modification. For the modification, as I mentioned, just to dry out the soil and stabilize it. Okay? And the lime is an excellent choice for the soft short-term modification of the soil. And the lime can be modified almost all fine-grained soil, but most dramatic improvement occurs when it's clay with high plasticity. As I mentioned earlier, this is the plasticity is going to reduction of the moisture holding capacity, swelling reduction, improved stability, and the ability to construct a solid working platform. Sometimes, when the soil is very soft, there are 2 methods. One is like a dry mixing method, and then shallow mixing method and the drip mixing method. Sometimes when the soil is really soft, use of cement or lime, and then mix it together. And the shallow mixing, just a little bit strength is increased, cure for 7 days or 3 to 7 days. And then when it is strong enough to hold that equipment, at least different boring machine and other, then you go there and then making a column like for the deep mixing for different, making a strong column, either cement or lime. So deep mixing column. Okay. So benefit of soil stabilization include substantial increase in the rational modulus values by factor of 10 or more cases, improve the shear strength. So, and then continuous strength gain with time, and then also long-term durability over decades. So again, we need to check. So when the soil is stabilized, so we need to go and check, do the test, how much the strength is improved. In the lab, generally, we do the UCS test, we do the CBR test, also to see the effect of dynamic load, we do generally resilient modulus test. The line stabilization should be considered when the plasticity is more than 10, plasticity index is more than 10, or percentage of passing number 200, that is 0.075 millimeter is 25%. Okay. So requirement of line stabilizations, the right combination of the material, adequate lime to keep polyuric reaction going, adequate strength to resist freeze thaw, and adequate compaction and moisture. There are a few things you need to check. Evaluation of line stabilizations, as I mentioned, the Ellis and Grimm's method. So what you need to do, first you add soil and different percentage of lime and see how much is the pH. So it's a quick test. So 12.5, that is the minimum amount of lime is required. So and then you need to add more maybe, and then see when it is stable, pH is almost stable, then that is the minimum requirement. Optimum moisture content, you can find out also. There's some standard proctor test, and you can find out. And the ECS test, so minimum is for like 100 psi, okay, the pound per square inch. So for ECS strength for stabilized soil. So again, so we need to check that. So mostly it is 50 psi, 50 to 100, depending on the situations. And there is a standard code you need to use for the stabilized soil. So this is some example like how we can use this line column. So there is a line column, and then people are constructing on the top of there is a lightweight structures. It can be for embankment also. You can construct on this line column, and then it can be the same thing. The line column, there is an embankment on the top. It can be used for ground anchor, and there is a sheet pile wall and the ground anchor also. It can be used using this line column. And then there is you can use that footing or foundation also. So there is a chart over here. This is a Dunlop chart, okay, that can be used to calculate how much percentage of lime, depending on how much the thickness of the pavement you need to know, and then also you need to know the CBR values. So Dunlop design, they developed a design chart for clay subgrade modified with either lime or cement. With CBR of 5 or less, okay? And then noted that if the lime is being used, stabilized clay subgrade can be assumed that some tensile strength to develop the modified layer. So here, this is the chart he will develop. So over here, so the chart for the design chart of pavement of 150 millimeter thick of lime modified subgrade. So there are three X, Y, and Z, 3 different coordinates, and then also lime modified CBR. And the subgrade CBR, you can calculate. So what you need to do, and then also you need to know that how much it is design load for the pavement, and then how much should be the granular cover, how much should be the base and sub-base thickness. All these things you can easily find out from this graph. So first thing is what I need to do, select a sufficient lime stabilizer to give 18 days CBR, at least 25%. So and then from quadrant A, you need to find out how much is the CBR of the modified method over here. So first thing you need to check that the quadrant A at how much is the cover you need, how much is the subgrade value you need, okay? And then from there, how much is the modified CBR value you need, and then from there you just go down and you can find out depending on the design load and calculate how much is the granular cover you need. So the process is given over here, and from here easily you can calculate basically how much is that. So how much is the granular cover you need for this lime stabilized soil? Okay. So I'm not going to go in detail, but you can easily find out all these different quadrant A, B, and C, and then you can find out how much is the. This is for the subgrade soil CBR. This is for the subgrade soil with the lime modified. This is the effective CBR for the design load, and you can find out how much is the cover required for the lime stabilized soil. So this is the same thing again. So now the second one is, third one is basically we talked about cement, we talked about lime. Now these are the different other stabilizers like a blast furnace slag. So this is the waste from a steel industry, and this is if it is grounded to fineness, approximately the same as cement, so that can be used because so this is a coarse material. Sometimes people use, that's why you call it ground granulated blast furnace slag, so GGBS, and then basically you are increasing the surface area is much more reactive. So also here, you see the chemical compositions. Is calcium is the again 36% calcium, silica is 36%. The calcium is the more binding agent, right? That's more, and so basically you see the rapid cooling create and more vitreous with high reactive slag, and slow cooling in crystalline or almost inert. So basically, again, if it is more amorphous, it's much more reactive. So how you can find out this amorphous and crystalline? So again, you need to do the chemical composition test, either using X-ray fluorescence spectroscopy. So you need to take some sample with microcrystalline wax, and then pass the X-ray and see how much is the percentage or different percentage of different chemical composition from X-ray fluorescence spectroscopy. So basically, it will give some signals or values, the peak, and you need to check that, run the actual sample, the actual silica, alumina, iron, pure one, and then you see how much is that. From there, you can calculate X-ray. So now these days, you just automatically the instrument will give you. So basically, the XRF you need to do XR, and then what are the different mineral forms? So that one you can. So how do you know this line and amorphous? So from the X-ray diffraction analysis, you can find out. And X-ray diffraction analysis also will tell you what type of mineral forms after this chemical reaction. That is the test you need to do, and then also do scanning electron microscope to see the microstructure. So there are two tests generally we do for X-ray diffraction, and then also scanning electron microscope. So blast furnace slag cannot react with water in itself. It needs some activation. So like a pozzolanic material, COH also from cement or lime can provide activation, but alkalis and sulfate can also be activated. Once the activated reaction takes place, largely spontaneous due to its own calcium reactions, it's a pozzolanic material. So you add water and lime, then the reaction starts. And main product, again, the same as other for lime or cement, calcium silicate hydrate gel, and and then the calcium oxide and silicon oxide ratio is important. Reaction is temperature dependent, and the higher the temperature, faster the rate, and the mixing lime or cement can help raising temperature and speeding the reactions. Fly ash is again another industrial product, coal-based thermal power plant. So it's most of the time these particles are very spherical, and people are using for different purpose, for using in a cement or small soil stabilizations. Because if you use in cement, so the cement in concrete can be more flowable. But sometimes these particles are hollow, and that is called sinospheres particles. Sometimes there are some particles are inside the hollow particle, there is another particle, some of pleurosphere. So that is also a problem. If you use in concrete for the soil, you can use it. So here the properties are fineness, vitreous content, and the loss of ignition, the unburned carbon. If there is unburned carbon is more, that is not good. So and then vitreous content normally between 60 to 90%. Higher the vitreous content, better is it. So again, we need to see that the chemical composition. Again, here the calcium oxide is the main component, right? For the glue is that holds together is 1 to 40%. So here there are two types of fly ash you need to know: class F and class C. Class F is pozzolanic; it has less CaO. But class C fly ash has more CaO, so that is more calcium. We need more calcium, right? Because the cement and lime is more calcium. So if you want to use fly ash, better to use class C fly ash. So that is much more reactive. The problem is sometimes, if you use in concrete, class C has more sulfur also. So then if if you use in concrete, the problem is the sulfur will form reacting with the water, forming sulfuric acid, and then again it will react with the reinforcement, and that is not good. And it will corrode the reinforcement. So we don't want that. So again, there is a concrete thing. So people are using, but the reaction mechanism is the same, whether you use in cement, in soil or cement in concrete. They're the same alkali silica reaction, calcium silicate hydrate, calcium aluminate hydrate, or actinic hydrate. So again, you need to understand the class F and class C. You need to do first X-ray fluorescence spectroscopy, find out what are the different chemical compositions. Most of the cases, the class F is the calcium oxide, silica, and alumina. Silica, alumina, and iron. If it is more than 75%, that is class F. If silica, alumina, iron is less than 75%, less than 70%, mostly or 50%, so then it is called class C. But the calcium is more in that class C. Calcium is less, nearly 5 to 7% in class A fly ash. So hydration reaction is the same thing again. Reaction is slow, but it will increase in later stage. So again, when the cement or lime reacts with water, it forms calcium hydroxide to turn either calcium silicate hydrate or calcium aluminate hydrate. Reaction is temperature dependent. And also is, again, you see the fly ash is very heterogeneous. So again, you need to characterize the first, what type of fly ash, whatever. Again, it depends on what type of coal you use, degree of pulverizations, temperature of the furnace, and the collection method. So there are not only fly ash, there are bottom ash. There are sometimes the fly ash and bottom ash mixed together, add with water, and then pump it to the lagoon. There's the lagoon ash. These properties are also getting changed. So again, calcium hydroxide plus silica, the calcium oxide and calcium silicate and hydrate. So calcium CSH. This is with alumina, it is formed the calcium aluminate hydrate. So we call it CaH. So polymer reaction at time is temperature dependent and may continue for a long period of time. Sometimes, if you need the strain quickly, you need to use cement or quick setting cement, or calcium sulfoaluminate cement. But if you need, slow reactions, we don't need the strain quickly. So you can use fly ash or any other material or GGBS. But in long run, the strain will be almost close to that fly ash or GGBS. Or cement. So again, there are several relations are here. You can calculate how much is that. There's a major component, the silica, alumina, iron. If you calculate that calcium oxide percentage divided by the silica, alumina percentage, if it is more than 1.75, then it is better. Such that the order of reaction takes place, the hydration modulus must be 1.7. So basically, you can see here, calcium oxide should be more, right? So if it is the numerator, it should be more than 1.7. So the calcium oxide should be more. Okay? So this will give you a little bit of guideline. Then the silica fume. This is another stabilizer. So over here, the silica fume is basically the manufactured metallic silica. It's very fine, and so the filter dust is called sometimes very silica fume is very fine. So it's considerably more consistent than the fly ash because fly ash has different types. So unlike fly ash, it contains some unburned carbon and CaO. Unburned carbon is not good. It's inactive, inert, and it's not reactive. 1 to 5% silica fume is commonly used, but we have to be careful while using this silica because it's so fine. If you inhale it, and then it will be a problem, and then the silicosis and other disease may happen. The polymer reaction is similar to fly ash, but occurs more rapidly because it's very fine. Okay, and the reaction is highly temperature dependent. Most of the cases, the reaction takes place when the temperature is more, right? So here, and the silica fume from metallic silicon manufacturers, from ferrosilicon manufacturers. So mostly the silica fume is mostly silica. It's 94 to 88%, 98, so it should be 94 to 80, 98% should be, and then 86 to 90%. Mostly the silica. The calcium is very less. So everything is very less except the silica. Okay. Again, stabilizer types, a wide variety of material. You can use it, as I mentioned already, the Portland cement, lime, asphalt, chemicals, salt, and other techniques. So we just talked about only few. And how selecting a stabilizer type depends on a number of factors. You need to see the particle size division. We need to see the plasticity index. We need to see the availability of the material, of the cost of the stabilizer. We need to see the appropriate construction equipment and the climate. So a lot of things you need to check, and you need to choose that what type of admixture or stabilizer you need to use. So these are some guideline, formation of hydration products over time. So obviously the stiffness is going to increase, setting, solidification, hardening is strength gain. So what is happening over here in the clay, particles of water, if we add ordinary Portland cement or slag, so what is basically the reaction is polymerase reaction takes place, hydration takes place, alkali activation takes place, and final product you see here, calcium silicate hydrate or calcium aluminate hydrate or calcium CaSH, calcium aluminate silicate hydrate. These are the few things is forming. Also over here in hydration products, calcium silicate hydrate. So basically, these are the reaction product is formed. And how do you know what type of mineral is formed? So you need to do the X-ray diffraction analysis. So you pass the X-ray and then see how much is the intensity, and you need to find out that the 2 theta using the Bragg's law, n lambda is equal to 2d sine theta. From there you can find out how much is the 2 theta and then what peaks are formed. So this is fixed for a particular mineral. So you need to know either JCPDS search bench program. So you can find out that for these 2 theta, what are the minerals? So you can find out from there, and then you know what mineral exactly. So, and then also most of the time we use the 3 strong peak, and then also you can identify the minerals using manually. Also, there is if you know the despacing, if you know the 2 theta. Manually, also, you can find out that what type of mineral is formed. This is another guideline also, Anberg and Justin. So this is, you see the binder, quicklime, cement, lime, or slag. So what is happening ultimately, is different reactions, hydration reactions, alkali activation, pozzolanic reactions takes place. And ultimately, it is forming the calcium aluminate silicate hydrate or calcium silicate hydrate or calcium aluminate hydrate. Or calcium silicate hydrate over here, calcium, this is etrigite form, and calcium aluminate. So these are a few different, so etrigite or monosulfate aluminate or trisulfate or monosulfate aluminate over here. Then, so properties of the stabilized soil. So the soil binder mixture depend on so many factors, as I mentioned. So you need to characterize the hardening, hardening binder. So now we need to characterize the stabilizer itself. Type of binder, quantity of binder, how much quantity you need to add, additives you need to add or not, and the quality of the binder and quantity of the binder. Characteristics and condition of the soil. So now you need to characterize the soil itself. So physical, chemical, and mineralogical properties, mostly for the clay. How much is the organic content present? If the organic content present, then the cement or lime is not going to react much. So I'm going to talk about that maybe in the next class. pH of the pore fluid is very important. You see the pH is increased when you use lime or cement. So alkali-acidic reactions, the reaction then it is much more reactive. Water content is important. Curing condition, its temperature is important. Curing time is important. That's why with time the strength gain. So 7 days, 14 days, 28 days, 90 days, if you study for long term. Humidity is important, and the wetting, drying, and freezing time. So obviously, you check the durability. Mixing conditions. So how we are mixing this soil? So using different types of mixing blades. There are different types. Degree of mixing, how much time you are spending for mixing. Sometimes even if you wait too much of time, then it will be a problem also, because the mellowing time should be, it should not reach that when the reaction already started, So, and then time of mixing and remixing, and then how much quantity of mixing water you use. So again, all these things you need to check before you go to the actual site for field mixing, So you need to do the lab test first, and then go to the site and do for the field mixing. And again, as I mentioned, there's the shallow mixing and the deep mixing also. So this is Cardinetol, 1976. They have a different classification. What type of stabilizer are you going to use? So depending on the particle size, right? So less than 200, that is 75 micron, 25, and the plasticity index less than 10 and 20. So you can use either cement or lime. If at-bug limit also you need to check, the liquid limit test mostly. And if you see that the particle size distribution percentage passing more than that, then obviously and plasticity index of the index is 10, less than 30, more than 10, less than 30. So depending on the situation, and you can easily calculate. You have an idea that what stabilizer is more suitable. So again, as I mentioned, that the cement is good for all type of soil. Only thing is, but more suitable for granular type of soil, sand and gravel. For clay, you need to add more quantity, and then the cost will go up, right? Lime is again, you need to use the optimum lime content or lime fixation point first. You need to determine and then use that. So 6 to 9 or 10% maximum. If you use more lime, the strength will go down. For fly ash and GGBS and other combinations, so we need to do test, and then only you will know exactly what is the optimum value. Okay? You need to do a lot of trial and error. Then U.S. Army Corps of Engineers, they have there are area that like this type of different area for area 1A, 1B, 1C, area 2A, and 2A, 2C, and 2B, and area 3. There are area 2A, 2B, 2C, and 3C. There are different demarcation and major soil groups. So basically, the sand, gravel, and fine-grained soils over here, and you can easily find out. So 1A is the area is basically SWSP. So basically, this is well-graded sand or poorly-graded sand over here. 1B is a mix, dual classification over here, you can see. And 1C is a silty sand or clay sand or silty sand and clay sand mixture. So basically you see the 1A is more gravel, correct? Sand and gravel. So over here in the more granular type of soil. And then you can use different type of whatever stabilizer you can use over here. SP, the bitumen or Portland cement or lime cement fly ash. And if this is like silty sand or clay sand, you need to use the Portland cement, lime, and lime cement. So this will give you an idea depending on the plasticity index and the particle size division. So whether it is well graded or poorly graded, and easily you can find out from there. And what type of stabilizer. So again, these will give you just guidelines. So you need to do the actual test for a particular type of soil, what type of stabilizer is more suitable. So this will give you a range and idea, but you need to do the actual test to find out. So this is again for the area 2A, 2B, 2C. So all these things are mentioned over here. So 1A, 1B, 2A, 2A, 2B, and 2C. So all these things are mentioned over here. And then which one is bitumen we can use? You can use Portland cement, you can use lime cement fly ash. 2B, you can use like a bitumen, Portland cement, lime with lime cement fly ash. So again, depending on the plasticity index and depending on the particle size distribution. And the area 3, again, this is for mostly the clay, high compressible clay or low compressible clay, or highly compressible silt or low compressible silt or highly organic soil. So again, you need to use the Portland cement. Or if it is like this, highly compressible, low compressible, clay, then you use the lime. For organic soil, it's different thing. Again, we'll talk more about that. The organic soil and peat soil is much more challenging because it has fibers, it is acidic, it is too much of water content, and to stabilize this type of soil is much more challenging. So I'm not going to go here, National Lime Association. So lime content generally increase, as I already mentioned, the lime fixation point you need to check. And sometimes, we can increase, first you increase a little bit of lime and just modify the lime so that, modify the clay. And then you add some more lime just for the reaction, okay? So, and as I mentioned, there is a Dunlop chart to find out if you want to design a pavement, depending on the how much the cover material you need to use. Soil bituminous reactions, obviously, the bitumen generally used for the pavement. Basic principle of this is waterproofing or binding. By waterproofing, inherent strength and other properties could be retained. Most commonly used material, the cardback or emulsion, and a layer can be used for the subbase or base coats for all the roads for environment. So basically, selecting the correct stabilizing agent, there are a few things you need to check. Particle size division, as I mentioned in the table earlier. We need to check the particle size division. We need to check the Atterberg limit. So two things you need to check, and then also there is a figure over here. So this figure it will guideline of this. So based on that, so basically the particle size division you need to check. So basically, what did you do? Initial guidance in selecting stabilizer, and then also you need to check the climate and drainage. So also you need to check the climate and drainage. In the wetter areas, moisture content prevents the material. So in that case, cementitious binder usually preferred. Lime is suitable for, as I repeatedly, cohesive soil, particularly when it's initial agent or dry out the material. So that is not stabilizer; it acts as a modifier. Using emulsion in cold, dry climate required using cement and lime facilitated moisture removal from the emulsion between the stabilizing process. So these tables will give you a guideline again, plasticity index and the particle size division when there's 25% passing more than 200 number of sieve, less than 200 number of sieves. So these blocks, so basically is here, the dark light brown is the most suitable, usually suitable. If it is a black dot, black color, this is not doubtful, and this white is not suitable at all. So basically, you see here for the line, just for example, this is the plasticity index is less than 10, and more than 25 is passing 75 over here. So that's doubtful, right? So this is more granular type of soil, right? So when you go on this side, it's much better. Okay. So and then here, if the plasticity is increased, the liquid limit is more. So obviously in that case, that is suitable also. Okay. So this will give you an guideline from the particle size division, and then the plasticity index, that is liquid limit minus plastic limit. Also, the Texas DOT, they also have that similar type. Sieve analysis, the basis is sieve analysis and Atterberg limit test. Less than 25% passing 200 sieve and plasticity index is similar type of chart you have seen. So they use, like, if it is less than like this, so you can use cement and fly ash or asphalt or lime. Cement, lime, fly ash, or combinations. So these are the different, like a guideline. Again, I'm telling you need to do the test, actual test, and then find out how much is optimum quantity. Okay. So these are the different guidelines. So now also when you're doing this test, you need to find out that the different Proctor tests, obviously. And then sometimes when you use lime, you see lime 0%. If you use lime, so density is decreased. Okay. So it's not that the density all the time will increase, because when immediately density will decrease, it depends on the specific gravity of the sample. So if the specific gravity of the lime is lower than the specific gravity, again, gamma D is equal to specific gravity gamma W by 1 plus E. So from there you can easily calculate. So basically, sometimes it is density is decreased, but with the pozzolanic reaction later on, the UCS value is going to increase. So two things. One is density, how the density is decreased, and then also different type of material. So if you use sometimes GGBS or other material when the specific gravity is higher, in that case, if you add like a density is going to increase also. So depending on what type of material you're going to use, it depends on the specific gravity of the material. Sometimes the fly ash is specific gravity is lower. When you use fly ash, generally density is going to also decrease. But when you reaction takes place, then again the strength will go up, the UCS strength. So suitability, again, you need to check. The lime works best for clay, especially though with moderate high plasticity, less than 15. Plasticity in this is less than 15. Due to lack of aluminum and silica in silt, granular pozzolation do not take place. Therefore, lime does not work well for the material. So granular material is not good. In order to stabilize silt and granular materials, so pozzolanic admixtures like fly ash need to be added in addition to lime. And then also the little suggested that you see this classically what type of stabilizer is good. And again, also you need to check that the sulfate concentration, if it is more than 7,000 to 800 ppm, lime can be used. Lime can be used with sulfate concentration. But as I mentioned, if you use cement and a lot of sulfur, then it is not good. Right? But lime can be used up to that percentage. It's less than this. So again, minimum UCS strength. There are several criteria: 7-day strength, 28-day strength, UCS strength for the base course, and then this is in PSI, pound per square inch. Flexible base course. Sub-base course is lower bottom. The base sub-base course, base course, and surface course. So sub-base, most of the time, the native soil is below this, the base sub-base course basically. So and then we need to stabilize or improve. For the rigid pavement, obviously the flexible pavement is the asphalt one. The rigid pavement is basically the concrete pavement, and the strength, you need more strength compared to that for the flexible one. Okay, so. Portland cement, I'm not going to. There are different type of cement also available, as I mentioned. So there are, you see here, type 1 cement, type 2 cement, type 3 cement, and then these days, depending on your requirement, you can use that. Sometimes there are sulfur-resistant cement. Sometimes we need quick setting cement. Also, you can use, and then also if you need the strength very quick. You can use like calcium sulfaluminate cement also. For screening test of organic matter and sulfate. So again, if most of the soil, if there is an organic matter, we need to generally get rid of that organic matter and also sulfate. Tests are generally detected for these materials should be conducted if there is a presence of suspect. So we need to do that. And also pH, we need to do the test for pH. 10:1 for the soil and then and cement, 15 minutes after mixing, and if you see where it's 12 or more. So again, like Eddy's and Grimm's method you mentioned for the lime, the same thing also you can use it. For the sulfate, sometimes because of ectringite formations, there is some problem. The sulfate clay reaction causes deterioration of the fine-grained soil because of the ectringites. So we need to test that clay soil first. How much is the maximum sulfate content is there, and then also the use of cement in fine-grained soil contains more than 1% sulfate should be avoided. So if the sulfate content is more than some ppm level is fine. If it's more than 1% sulfate is there, then don't use cement. Okay. There are some guideline also there for how much quantity of design cement content you need to use. So 100 times A is equal to 100 times B times C. So depending on B is equal to percentage passing, number 40 C expressed in decimal. C is the percentage of cement required to obtain the PI minus 40%, number 40 material. expression. So again, this will give you some guidelines. Earlier you have seen this is ASTM 425, 423 and 425. So you can find out how much is the optimum quantity of cement. Most of the time, people use here in Illinois, depending on the type of clay, is 5 to 10% maximum. Because more cement, you get more strength, and then obviously the cost will go up. So that's the reason people don't use too much of cement. This will give you some guideline, as I mentioned, like if you use the well-graded gravel and sand as per USCS classification. These are all USCS symbols, already. This is 5%. You can use if it's well-graded, so 5% to 6%. If it's poorly graded, is a little bit more. So well-graded soil is, the soil has all the different size particles, right? So we need that. The compaction will be good, strength will be good. And then it's poorly graded, so we need a little bit more. If it is a silty type soil, silty gravel, silty sand, clay gravel, all this, and the dual classification, the percentage finer, 7 to 12, more than 5, less than 12. So then there's a dual classification system. So in that case, it's 7%. And then that highly compressible soil or silt and clay. So then you need to use a little bit more, 10 to 12%. So depending on again, this will give you a guideline only. Okay. So, and yeah, I think that's all for,
Thank you, sir.
All
Do
right.
anyone have any questions? Please ask.
Anyone has any question?
Anyone have any questions?
So I have not explained much on this other stabilizer, like in much more detail on the reactions. I just mentioned this very basic thing, what is happening, what are the tests, chemical combination you need to do, and then also basically the particle size and the liquid limit test, you will know what type of, and then you see the chart, you can easily calculate pH test you need to do, and then cement and lime and fly ash. If it is a polygeneric material, so you need to add a little bit of lime and fly ash, lime and cement, then the reaction is going to occur. And then, you need to do several trial and error tests and find out the optimum. The only thing is the lime is you need to have a lime fixation point. More lime is not good. So more lime, the strength will go down. Okay.
I think they don't have any questions, sir. So can we take a 15-minute break and then we will start at 9?
Okay. All right.
Okay, sir. 1
Okay.
minute, sir. Someone have asked one question. What is it? Regarding lime stabilization
Yeah,
for
I can read
intensive.
now. I can see.
Yeah.
Expansion of clay, having higher plasticity, the addition of lime leads to higher moisture content compared to the untreated. Expensive clay. Yeah, I mean, if it is expensive soil, so again, you need to be. So again, if you use lime, so obviously lime, it will increase. So again, whatever test you're going to do, right? So if you do expansive index test or any other test, so first as I mentioned, the density, as I've seen the standard Proctor graph, where the lime is going to decrease, is basically optimum moisture content is increased basically. But when you prepare the soil sample, with time, it will be fine. Sometimes the pure lime is not going to help. So sometimes you need to add some lime, some other stabilizer also. Okay, so it depends. And then for durability aspect of GGBS, so durability again, I'll show you some results with some different mixture so durability aspect is basically what you do. You prepare a sample and then you do accelerated either freezing, thawing, or wetting drying and see what is happening. Basically, you need to see the volume change, there is a loss of mass, all these things you need to check. And then after how many repeated cycle, and then you can determine. Okay, so you cannot say that. Yeah, you need to do the test, and then only you can say how durable is that. Okay, does it make sense?
Sir, then we can start by 9 IST, 9 o'clock IST, means in
Okay,
13 minutes. Uh,
okay, okay,
okay, sir. In 13 minutes, we will be coming back here. Okay, sir.
okay. All right.
Okay. Okay. Thank you, sir.